Assalamu alaikum everyone. Welcome to this recorded makeup session. So if you recall the kind of stuff which we have completed in our previous class, we started counting and we talked about the fundamental three principles of counting, including sum principle, product principle, and complement principle. In this session, we'll be trying to complete counting, and we are starting with another principle which is called inclusion-exclusion principle. So let's try to recall this problem which we solved in one of our previous sections. So the question was that I have 32 students in one section and 35 students in another section of discrete math. Suppose I give the grade A to one student. So how many choices do I have in total? So what we did last time was that we applied the sum rule. We added 32 with 35. So 32 plus 35 choices were total available for me to award grade A. So now if I have 32 students in discrete math and 35 students in a programming course, and my basic stance of awarding grade A to one student remains same. So now how many choices do I have in total? Take a small pause and think on your own that how many choices do I have? So is this answer of 32 plus 35 correct? What about the students which might have been enrolled in both of the courses? So in this total, I might have counted some students twice. So if you recall the fundamental sum principle, the basic principle claimed that we add the cardinalities of both of the sets if those sets are disjoint sets. But in the context of a course which is discrete math and then there is a parallel programming course, there could be an overlap. So the overlap part is being counted twice. So in order to discount that part, so we are updating primarily our sum rule, and we call it inclusion-exclusion principle. So in order to find the cardinality of A union B, we add the individual cardinalities and we subtract the overlapping part, so that the students who were counted twice, once from a discrete math perspective and other from programming course perspective, they should be counted once. So in this as the recorded session for all the ICPs, I would strongly suggest that pause the video. So try to solve the ICP on your own and then move forward. So that will enable the understanding of the underlying concepts. So if you look at these two sets, A and B, so our task is to find cardinality of their union. So we add the cardinalities of both of the sets, but there's an overlap. So for example, if you focus on the sets, 7 and 9 are included in both of them. That means that 7 and 9 have it counted twice. So we need to subtract the cardinality of the intersection. If we have three sets, so we can update our inclusion-exclusion principle. So if you look at the Venn diagram on top, so blue parts are three sets which are overlapping with each other. So if we add their cardinalities, A cardinality of A plus cardinality of B plus cardinality of C, then we start discounting the overlapping parts. So cardinality of A intersection B is discounted, cardinality of A intersection C is discounted, and cardinality of intersection of B and C is discounted. But as a result, once we discount all those overlapping parts, we are completely ignoring this red part, which means that the elements which are part of this red part are not being counted in any of those components in counting. So we put it back and we add cardinality of intersection of all those three sets. So the same principle can be generalized to any number of sets. So if you apply this principle on this ICP, again, take a small pause in the video, try to solve it on your own. So you will add the individual cardinalities, then you will find the cardinalities of all those pairwise intersections and the overall intersection, and you'll manipulate them to find the answer. So if you look at the pattern which we have for three sets and the similar kind of stuff which we had for two sets in our previous slides, so in this particular explanation, we generalize inclusion-exclusion principle for n sets. So if we have to find cardinality of n sets, if they are disjoint, then we simply add up their cardinalities. But if we are not sure about the disjoint, then on alternating basis, we subtract the overlapping parts and we add back the parts which have been uh, completely discounted. So we put them back as we did it for the red part in the example of 3 sets. How many integers between 1 and 3, both inclusive, are divisible by 5 or 7? So the first attempt could be that you can take a small pause and try to figure out that how many integers are divisible by 5. And you can because we are starting with a layman kind of exercise, you can try to uh, limit the total range. So let's say we are interested in finding the number of integers which are divisible by 5 from 1 to 50. So the first element will start with 5, then 10, 15, 20, and up till 50. To count all of them, there is a beautiful relation between the total number of elements and 5. So another important point which you might have noticed over here, so the number of integers which are divisible by 5 from 1 to 50, that count will remain same if I include numbers from 1 to 51. That will remain same if I keep the count from 1 to 52. And that will only change when we touch 55, which is the next multiple of 5. So we create 2 sets. M5 is the set of integers from 1 to 300, which are divisible by 5. M7 is another set of integers from 1 to 300, which are divisible by 7. So M5 means multiples of 5, M7 means multiple of 7. And our task was to find their count, and then there was an OR relation. So we take union of both of them. But before we take the union, we find individual cardinalities. So individual cardinalities are computed as 300 over 5, and we take the floor of 300 over 5 because if you recall that example of numbers which are divisible by 5 from 1 to 50. So 50 over 5 is 10. So because 50 is divisible over 5, so irrespective of whether we take floor or not, our answer will remain 10. But what about 51? When you go for 51, 51 over 5 is 10 point something. So number of divisible integers from 1 to 50 will still remain 10. And that will remain 10 if we increase the range from 1 to 54 or 1 to 53. That will only change when we land on 55. So for that entire group, we are applying the floor function because our answer will remain same for a certain range. Same will go for M7. And when we think of cardinality of a set which takes care of intersection of both of them, there is 300 over 35. When we say both of them, that means the integers which are divisible over 5 as well as 7. So which means, in other words, we are talking about integers which are multiples of 5 and they are at the same time multiples of 7. So if an integer is multiple of 5 and 7 at the same time, that means that integer is multiple of 35. So that's why we divided it over 35. So now we know those 3 cardinalities, we plug them in our inclusion-exclusion principle, and we defined the cardinality of M5 union M7. So we plug in the answers and we'll be able to find the solution. So now I would strongly suggest that take pauses for each of the ICPs, solve them on your own. First one is somewhat quite similar to what we have just solved. The major difference is that it is focused on three kinds of sets. Create a set which is M5, first one is M3, then M5, then M7, and you have to find the cardinality of their entire union. So for the remaining 2 ICPs, 1114 and 1115, I would strongly suggest that first try those ICPs on your own. So if you had paused the video, you might have figured out the answer for I-level 14. So essentially, we are interested in computing the cardinality of M3. And sorry for the poor handwriting over here. So we are putting it with M5. M3 intersection M5 cardinality. So this set will contain all those integers which are divisible by M3 and M5. And then we are saying that we don't want to count those integers which are also divisible over 7. That means that the integers which are divisible over 3, they are divisible over 5, and they are also divisible over 7. So these are the ones which we don't want to include, so we need to exclude them. And so we put a subtraction sign between them. So this expression, if you succeed to compute the cardinalities of these two sets, you'll be able to answer level 14. So if you think of the solution of 1115, we are interested in the integers between 1 and 300, which are divisible by 7. That means that we are interested, one thing which we are interested in is the cardinality of M7. And then we need to subtract some cardinalities. For example, we don't want to include the ones which are divisible over 7 and 3. So this is the cardinality which we want to subtract from the total cardinality. We also want to subtract the cardinality of M7 with M5. Now, if you look at these two subtracted parts, there is a chance that we might have subtracted some elements twice. By twice, I mean the elements which are divisible by all three of them. So we need to put back those elements which are divisible over all three of them, M3, M5, as well as M7, because we have removed them twice. So this expression will give us, once we successfully compute the cardinalities of those individual sets, it will give us the cardinality of the desired set which we are looking for, which means the number of integers between 1 and 300 that are divisible by 7, but by neither 3 nor 5. Okay, let's go over another example. Find the number of passwords made from the characters A, B, F, and so on. So if you count the total number of characters over here, they are 10. Length of the password which we need to create is 10, but no repetition, which means that we are interested in some combination of all of these letters. So repetition of letters is not allowed, which means that each letter is going to be a unique one. So, but there is an additional restriction on that, and that is that no password contains the word golf, math, or boat. So we break down the problem into pieces. So we first count invalid passwords. Passwords containing golf. So take a pause, try to figure out that how many passwords contain golf, can contain golf as the substring. So treat golf as a block. By block, we mean that golf is now one component in the entire password of length 10. So it is taking length 4, and we have 6 remaining pieces. So golf is the 7th one. So the total number of permutations where golf will be the substring are 7 factorial. And as length of math and boat is also 4, so same principle will apply for passwords containing math or passwords containing boat. Their count will also be 7 factorial. So what about a password which contains both golf and math? So if you look at the total number of possibilities, golf is consuming 4 characters, math is consuming 4 characters. So we treat both of them as two separate blocks. So Gulf and Math are two blocks, and then we have two remaining spaces where we can insert two more characters. So in total, that gives us four possible spaces, and our number of possible passwords which can be generated using these two combinations, Gulf and Math, are 4 factorial. Same count will be for Gulf and board. What about board and Math? Treat board and Math as blocks, as we did in the case of Gulf and Math. Take a pause, try to figure out that how many passwords will contain both and Math together. So if you have figured out, you might have already observed that character A is part of both, character A is part of Math, which is not allowed. No, there is no repetition in the password, so we can't generate any password which will contain both and Math together. So their count is 0. So the total, so we applied the inclusion-exclusion principle. So the total possibilities were 10 factorial. We can generate all possible passwords of length 10 with no repetition. And then we discount those three different kinds of counts, which ended up in 7 factorial, because 7 factorial is the number of passwords which can contain Gulf, another 7 factorial for the passwords which contain Math, the third 7 factorial for the passwords which can contain both, and then we are putting back the 4 factorial. So Gulf and Math are being put back, and Gulf and both are being put back. They're being put back in the final answer. We don't need to put back Math and both because that's 0. Let's have a look on another example. So you have been given some news information. So for example, someone claims some statistics, and this is a like school report. So you are analyzing the school report as the boss of the school or as some external analyst. So 90 students in discrete math are enrolled. So the total entire population of the school is 90, and all of them are enrolled in discrete math. 60 out of them are boys. 60 students out of those 90 students are also enrolled in computer programming. From computer programming pool, 32 are boys. 56 students are registered in econ. 36 are boys in the econ group, and 34 are also registered in CP from within the econ population. The additional information we have is that 30 boys are registered in computer programming as well as econ. So what we do is that we try to model this as a set theoretic problem. So we create a bigger set, capital D, which is students in discrete math, which essentially represents all students. Set of boys is represented as B. Set of students enrolled in programming course are represented as P. Students enrolled in econ course are represented as E. And our task is to find G, those girls who are only taking discrete math. So our count is that how many girls are taking only discrete math. So we try to work with the cardinalities. So we start with the first line. The given information is that cardinality of D is 90. And out of those 90 students, 60 are boys, which means cardinality of D intersection B is 60. Now we go to the second line. So this says cardinality of the students who are enrolled in programming course are 60. Out of the programming course, from within the programming course, 32 are boys. So that gives us another intersection in its cardinality. 56 students are registered in econ, and boys who are enrolled in econ are 36. 34 students are taking econ as well as programming course. So we have now many cardinalities. The last cardinality which we model over here is that 30 boys are taking econ as well as programming. So there is 30. So we are interested in computing girls in discrete math. When we say the girls who are only taking discrete math, that means from the entire population of discrete math, we need to subtract the set which is of they are either boys or they're taking econ or programming course. Why are we taking union? Because those are the kind of exclusion criteria. So if there's a boy in a set, we don't need to count in the set of girls. If there is someone who is taking econ, does not need to be counted in our set G because that is representing girls who are only taking discrete math, and same applies for P. So we move from here to the cardinalities. We try to find cardinality of G, and we open up this union, B union E union P, using inclusion-exclusion principle, and we end up into this expression. So this is D minus, so after D minus, you can take this whole thing as a substitution of B union E union P. And we have simply applied the inclusion-exclusion principle. And we know answers of all of these individual cardinalities. So we plug them in, and the surprising thing which you will be able to observe over here is that we are ending up into an answer which cannot happen. So it says that -14 is the answer. So that cannot be cardinality of the set, because the smallest possible set is an empty set. Its cardinality is 0. No cardinality can be a negative number. So that means that the given information is not even correct. So if you are a mathematician and you analyze a report, you will always be able to figure out these kind of loopholes in the given information. Okay, so these are some general principles. We have used some of them, and some of them are derived from the ones which we've talked about. So for example, we've talked about the cardinality of union of two sets. So we apply inclusion-exclusion principle and we subtract the overlapping part. So if two sets have been given, their intersection, cardinality of their intersection will be less than or equal to individual cardinalities of those sets, and the answer will be flipped for union. And you can go through rest of the principles on your own. They are pretty intuitive. Okay, our next principle, which we are about to have a look at as part of our counting exercise, is Pigeonhole principle. So the principle is very intuitive and very simple. If there are more pigeons than the pigeonholes, so these boxes are representing pigeonholes. So for example, in this visualization, we have 1, 2, 3, 4, and 5 pigeonholes, and we have 6 pigeons. So if the number of pigeons is greater than number of pigeonholes, then some pigeonhole must have more than 1 pigeons. Right? So in 6, these 6 pigeons can be placed in 5 pigeonholes only if we allow repetition in one of the pigeonholes. So where would this be ever be useful? This has a lot of applications in our different applications of computer science. So for example, in the next course, when you'll be taking data structures, you'll be talking about hashing. So we compute probability of collision by using hash functions, and pigeonhole principle actually plays a quite interesting role in figuring out the chances of collision in hashing. Same way, we can use pigeonhole principle to prove that there cannot be a lossless compression of some size. Okay, let's have a look at some interesting applications of pigeonhole principle. So most of you might have played or seen people playing cards. So any set of, so in general, if you're not familiar with this entire card stuff, so types of cards are 4, and each type has 13 cards. So types of cards are 4. So if each type is called a suite. So if we have to choose 5 cards, then there will be at least 2 cards being fetched from the same pool. Why? Because there are 4 pigeonholes or 4 types of cards, and the individual cards which we have picked are more than 4. So at least one bucket, at least one pigeonhole should be containing more than 1 pigeons or cards in our context. Any set of 10 cards must have at least how many of the same suite? So if you think of 10 cards, if we try to scatter them as much as possible, we can't. So we start placing 1 card in each bucket. So we'll be done with 4 cards. We start placing one more card in each bucket. So each bucket is now containing 2 cards, but still we are left with 2 more cards. So that means that that's a leftover. So if we only think of 8 cards and we have 4 different types of cards, so 8 over 4 is the answer. But if we have 9 cards, we need to have at least one more card in one of the buckets, in one of the pigeonholes. So for 9, 10, 11, so the answer will remain that we need to place at least one additional card over there. So for that purpose, we apply 10 over 4. We take the seal of that thing. So number of cards of the same suit have to be 10 over 4, and it's C, because this answer will remain same for a particular interval. Prove that in any set of 13 randomly chosen people, at least 2 have the same birth. Take a pause, try to figure out on your own, does this claim make sense? If yes, how will you prove that the claim is true using pigeonhole principle? So if you have taken a pause, you might have figured out that there are 13 people. The possible months available to us where someone can have a birth month, they are 12. So there are 13 pigeons, 12 pigeonholes. So at least 1 month should have two people classified in that particular month. So at least 2 people will have the same birth month. Your task is to schedule 6 exams in different exam slots. Sorry, you have to schedule. You have been given 6 exam slots per day in an exam week, which is of 7 days. So in total, you have 6 times 7, 42 different slots. No 2 simultaneous exams in a room. So 300 courses have exams, and you need to schedule them. How many rooms are needed at the minimum? Take a pause. Try to figure out this problem in the form of pigeons and pigeonholes. So that we simply apply the pigeonhole principle, that 300 courses being divided into 42 slots, and its seal will give us the minimum number of rooms which are required. So we can generalize this principle. We have n pigeons, h holes. So n over h with its seal is the minimum number of pigeons which a hole should be having, which some hole should be having. In any set of 12 numbers in the interval from 0 to 1, there are at least 2 numbers x, y such that their absolute difference is less than or equal to 0.1. Now take off the numbers in the form of pigeons. So we have 12 numbers. They are pigeons. They need to be placed. So let's try to think in the opposite in that way, that how can we scatter the numbers in such a way such that their differences are there are no 2 numbers which will fall within the difference of 0.1. So if we start from 0 and we go up till 1, so from 0 to 0.1, then 0.2, 0.3. So we draw the number line. So including 0, we'll be ending up into 11 possible buckets. So when we choose when you choose 12 numbers, at least 2 numbers will fall in one bucket. Each bucket is representing a difference of 0.1. Another example, there's a party of n people taking place. So some handshaking takes place, which means some people shake hands with each other. A pair of people either shake hands once or they don't. Claim is that at least 2 people in the party shook the same number of hands. So the number of people is n. The possible number of shakes could be 0. That if there is a person who didn't shake hand with any person, then the possible number of handshakes could be 0. If a person has shaken hand with one person, it's 1. If a person has shaken hand with 2 persons, then it's 2. If a person has shaken hand with everyone else, then this number could be n minus 1. Now, if you focus on this set, its cardinality is n. So straight away, it does not give us any contradiction. We have n people. We have n possible handshakes. So all of them can be having different handshakes. Claim is that at least two people shook same number of hands. So take a pause. Does this thing make sense? We have same number of people, same number of handshakes. So how does this claim can be true that at least two people shook the same number of hands? If you have taken the pause, you might have figured out that there could be two possibilities. One possibility is that someone in the entire party shook n-1 hands. What does that mean? That means that that person shook hand with everyone else. So if that person has shaken hand with everyone else, then there's no person in the party which would be having zero handshakes, because this particular person in case one has shaken hands with everyone else. So the number of pigeons is n, pigeonholes is n-1. So hence at least two persons would have shaken the same number of hands if this case one happens. Case two is that no one shook n-1 hands, which means that there is a person which is actually complement or opposite of or negation of case one, that there's a person in the party who didn't shake hand with everyone else. That means that that person has missed some person. So if that person has missed some person, then there won't be n-1 handshakes. And again, our number of pigeons and pigeonholes will be n and n-1 respectively. So hence, at least two people would have shaken the same number of hands. Five departments, each with 100 students. The task is to find that how many students should be selected so that from some department, at least 6 students are selected. So we have 100 students, we have 5 departments. So n over 5. So n in this particular case is in this particular case is representing number of students. So we have 5 departments. Each department has 500 students. How many students should be selected so that from some department at least 6 students are selected? That means that we want to fulfill this expression according to the Pigeonhole principle, that n over 5 with its seal equals 6. And if you take away the seal, this means that n over 5 is greater than 5. And then we multiply this inequality with 5 on both sides, and that gives us that at least 25, more than 25 people should be selected to ensure that claim. So all the ICPs which we are going through over here is that I would strongly suggest that solve them on your own first and then move forward. All of them are ungraded as part of this recorded lecture. So this is another example. 100 people go from Lahore to Islamabad in 22 buses, each bus with 60 seats. So some bus must carry more than at least X people. So we need to find X. So we have 1,000 filled seats because 1,000 people are traveling, 22 buses. So what is the minimum number of people which some bus should have at least? So that will give us a seal of 1,000 over 22. And some bus must have at least Y empty seats. So the pigeons over here are the empty seats, and the pigeonholes are again buses. So we can compute the empty seats by multiplying 22 with 60. That will give us total number of seats. 1,000 out of them are occupied. The remaining part will give us empty seats. So that number over 22, and we take its seal, that will give us Y in this case. Prove that any set of 11 two-digit numbers must have 2 elements whose digits have the same absolute difference. Take a moment, take a pause, and understand the question first. So the pigeons are, so because we have to choose 11 two-digit numbers, so we have 11 absolute differences of digits in each number. Because 11 digit numbers have been chosen, Another two-digit numbers have been chosen. So digits, difference of digits in each number will give us 11 absolute differences. And the possible differences between digits, between different digits range from 0 to 9. So that count is 10. So hence we have more pigeons than number of pigeonholes. Hence at least two numbers will share the absolute difference of digits. Choose three different digits from 1 to 9. Write all orderings of those digits. Prove that among all the three-digit numbers written that way, there are two whose difference is a multiple of 500. So the number of integers that could be chosen over here are 9 times 8 times 7. So that turns out to be, this number is 504. And number of possible remainders when divided by 5 are the pigeonhole. So when we divide any number over 500, the possible remainders are from 0 to 499. So the number of remainders is 500. So if we have chosen if we have 504 total such numbers, divide each of them over 500, the possible remainders are over here. 0 to 499, which means that we must have to have at least two numbers, two integers. We can call them x and y, which will share the same remainder when divided over 500. That means that if you recall the basic division arithmetic, which I had asked you in the previous class to go over on your own, that if you think of an integer, let's say x, we divide x over 500. So we'll be having a quotient over here. So we'll have 500 q over here, and we'll subtract it and we'll get a remainder. So the possible remainders have to be from 0 to 499. So because our numbers are more than the possible remainders, which can be generated as pigeons, so there should be at least two numbers, two integers, x and y, which will be sharing the same remainder. So we can write this x using the basic integer arithmetic. We can write x as 500 cubed plus r. And more specifically, I can call it q1, quotient 1. We can do the same thing for y. So y can be written as 500 times, because we're dividing y over 500, some quotient q2 plus r. And why we are writing r and r in both of the numbers? Because the reason we are writing r and r over here is because r is the common remainder. They are sharing the remainder. So what we do is that we try to subtract x from y, and because we are interested in the difference. So when we say x minus y, it gives us 500 times q1 minus q2, and r get cancelled. So this difference is a product of the difference of the numbers is product of two integers. One of them is 500. So hence the difference is divisible over 5. The last ICP of Pigeonhole principle is that proof that among any n plus 1 numbers selected from a set of numbers from 1 to 2n, there are two that have no factor in common other than 1. So we use this fundamental lemma, which we have been using in one of our previous proofs, which we did before bit 2. So pigeons are n plus 1 because n plus 1 possible numbers are being chosen. And there's no integer which divides two consecutive numbers. So if we like alternate these numbers in S, we end up into S n pairs. So at least two numbers, there are two numbers that we'll be having two numbers that have no factor in common over here. Our next topic is permutations and combinations. So we have done some stuff related to permutations when we started counting stuff. How many ways to arrange the letters A, B, C, and D? So we said that there are 4 possible choices for the first placeholder, then 3 possible choices for the second one, 2 for the third one, and then we're left with only 1 choice. So we call it 4 factorial. How many 5-digit codes are there with no repetition? That gives us, because there are 10 possible choices for the first placeholder, then they keep on decreasing. So 10 times 9 times 8 times 7 times 6 is the number of 5-digit codes with no repetition which we can generate. How many ways to arrange n letters? We can generalize the first one, that is n factorial. How many R-digit codes are there with no repetition from n characters? So we just need to generalize this 5-digit code stuff. So if you focus over here, our total number of choices were 10. So we started with 10, we went back to 5 plus 1. So over here, we are generalizing 5 as R, and the total number of possible characters which are available for us are n in place of 10. So we start from n, we go back to times n minus 1 times n minus 2 to n minus R plus 1. So a permutation is possibly an ordering or arrangement of some given objects. Number of permutations of n objects are n factorial, and we specialize a particular situation out of generalized permutations. That if we are talking about some R elements being picked from a pool of n objects, then we call it R permutation, and that gives us this count, which is n into n minus 1 goes down to n minus R plus 1. So we write it as a function P and R. P is for permutation, n is the total number of objects given to us, and R is size of each permutation. So what is the total number of R permutations which can be generated from n objects, or what is the total number of n orderings or arrangements which can be generated from n objects? So essentially we have R placeholders, R boxes, and our task is to fill those boxes. So when we start, we have n choices, the number of choices start decreasing, and our last in the last box we'll be having choices of n minus R plus 1. So the small thing, because if you look at the rightmost term getting multiplied in this product is n minus R plus 1. So the one like lower term would be n minus R. So n minus R going down to 1 are the ones which are not being counted. So when we generalize it, we write it as n factorial or n minus R factorial. So let me try to explain it later further. So the kind of stuff which is missing from here, if we have to make up this entire thing as n factorial, so this part would have been, this term is essentially n minus R plus 1. Then we'll be going to n minus R, then the previous one will be n minus R minus 1, and it will go down to 1. So this part is essentially n minus R factorial. So we have to get rid of this part because our number of boxes are limited to R. So we write as n factorial over n minus R factorial. I have 5 students named A, B, C, D, and E, and I give prizes $5 and $3 to 2 students. So how many choices do I have? So because I have to choose 2 students, the first student will be awarded with 500 prize. The second will be chosen 300 prize. So for example, if I choose A and B, when I choose A, B, A is going to get 500 prize, B is going to get 300 prize. But if I choose B, A, B then will be getting $500 and A will be getting $300. That means that A, B, and B are not same. So we write as permutations in general are the orderings. So order matters. So out of 5 students, we are interested in 2 students. So we are looking for the number of 2 permutations. from a pool of 5 objects. But what if I have 5 students and I give grade A to 2 students? Now, order of selection does not matter, because if I choose A, B, so both A and B are going to get A grade, and if I choose B, A, then again they are going to get the same grade. So the net impact is 0. So A, B, and B, A have to be treated in the same way. But if we apply our fundamental principle of permutations, so we'll be computing this as P52, our answer will be 20. But what we know is that each pair has been counted twice. So, but these are so these ones, the permutations are the ordered pairs. So what we do is that each unordered pair has been listed twice or 2 factorial times. So what we do is that we divide our total number of permutations over 2 and we get 10 unordered pairs. How many subsets of size 5 are there for the set from 0 to 9? Take a pause, try to figure out. If you have taken a pause, you might have already figured out that we are talking about subsets. So in sets, order does not matter. That means that in the first go, we can compute the permutations, but permutations are like writing each set multiple times because order does not matter, and these are the ordered arrangements. So the number of arrangements or orders of 5 digits is 5 factorial. So we divide this P10.5 over P55, and that will give us the number of subsets, which means when we say number of subsets, that means that we are talking about a collection of objects where order does not matter. And if you look at this last permutation, this gives us a very interesting result. So our n was 10, our r was 5. So we wrote it as n factorial over n minus r factorial times r factorial. So when we generalize it, we call it R combination. So combination is another collection of elements, but in combinations, order does not matter. Or in other words, we are talking about subsets. So R combination is a subset of size R. So if you have to count number of R combinations from n objects, then we write it as PNR over R factorial. Or if you look at the right side, so this is the new notation which we are looking at. This is for combinations. We call it n choose R. So n choose R means that we are talking about number of combinations, more specifically number of R combinations of n objects. And this expression NR is also called binomial expression. So we'll be reading it as n choose R, which essentially gives us number of R subsets from a pool of n element set. So let's try to have a look at this formulation of computing number of R combinations. N choose R in general can be written as the one which is given on the top. So we are interested in finding number of 0 subsets, which means that how many subsets of this set contain no elements. That means that we are talking about 4 choose 0. So we plug in, so R is 0 over here. So we plug in our basic formulation, we end up into the answer 1. If you jump to the last row, that says number of 4 subsets of this set, because a subset of size 4 will be the set itself. So we write 4 choose 4, and our answer is 1. And we know from our basic set cardinality concepts that for any given set, the smallest subset is an empty set, so its count is 1. The largest subset is that set itself, and again count is 1. So for this set of 4 elements, we count number of 1 subsets, which we compute 4 choose 1, it gives us 4. Look at the second last line, we compute number of 3 subsets, and we find 4 choose 3, the answer is 4. So you might have, and then you can compute 4 choose 2. So if you look at all these 4, 5 answers, there's a beautiful symmetry over here. We'll talk about this symmetry later as we go along in the course. Focus on the ICP, take a pause. How many 3-bit sequences, 2 zeros and 1 1? So one crude way of doing things, as we have been doing, could be that there are 3 possible positions. We can like try it using our conventional way of doing things. which we have been using in our previous class as well. So let's say we have three placeholders. So three possible ways to put the first zero. So we go with three. Then for the second placeholder, we have two possible choices left with, and for the last one. So this answer gives us 6. But there is a problem in this answer. And the problem is that if you start writing, so for example, let's try to enumerate these three red bullets. When we say three possible positions to put the first zero, that means that the first zero can be the first digit, and the second and third digit have yet to be decided. Or the second digit, the first zero can be the second digit, and first and third positions have to be decided. Or the first zero is the last digit, and first two positions have to be decided. Then we go to the second bullet, two remaining positions to put the second zero. Now we have two choices. One choice is, let me change the color. So one choice is that if I look at the first possibility, I can put the zero over here. Or from this one, I can generate a possibility that first zero remains as it was, but the second zero is placed at the end. If you look at the second row, we can put the second zero over here, or we can leave this first place as it is and we put second zero at the end. If we look at the third possibility, the second zero can go at the start, or it can go, we can leave the first place and it could go to the second position. Now, in all these different 6 settings, we have only choice left for 1. So we place 1 over there. So this is 1, 1, 1, 1, 1, and 1. Now, if you count the total number of possibilities, that actually gives us 6. But the problem is that there are many substrings or many binary sequences which are same. So for example, this is 0, 0, 1. This is also 0, 0, 1. This is 0, 1, 0. We have 0, 1, 0 over here. So we are left with 2, and then these two are same. So essentially, we have these 3 unique settings, string 3 bits, 3 unique bit sequences. So what we do is that we apply combinations, choose 2 positions for 0, and 1 is forced automatically. So we go for 3, choose 2, and that gives us more intuitive answer. Because when we go for 3 times 2 times 1, that means that we are restricting the we are restricting the order between 2 zeros, which does not matter, right? How many 7-bit sequences with 3 zeros and 4 ones can be generated? Choose 3 positions for zeros, and the ones are forced. Or equivalently, we can choose 4 positions for ones, and then the remaining positions are forced. This is another example of counting with combinations. So this whole list is like terminology of poker. There are 2 card decks, 5 card hands, and 4 possible suites of the cards. So 13 possible values from 2 to A. So there's a term 4 of a kind, 4 cards of the same value. How many different poker cards with 4 of a kind are there? So 13 choices for the value of the 4 cards, 12 choices for the value of 5th card, and 4 choices for the suite of the 5th card. That gives us this answer. Full house is another term, 3 of one value and 2 of another. How many different poker hands with full house are there? Explore this answer on your own if you have some fundamental understanding of the game. Otherwise, you can opt to skip this example if you don't have any idea that how poker is played. The last example for this session, the school committee of 8 faculty members has to be formed subject to these rules. Committee should have 5 and 3 members from EE and CS department. EE department has 30 and CS has 20 members, which means that for the committee, we have to choose 5 people from 30. That will give us representation for the EE department, and then we have to choose 3 people from 20, which will give us representation for the CS department. and then their product will give us the total possible settings in which the query can be found. That's it. I hope the content is understandable, but if not, please feel free to get back to me. Thank you for your support and patience.